So for example, I can, and this is, you know what is that? This is a unit vector, huh, from elementary mathematics, you know. Actually, they are the unit vector over the axis x, y, z. Huh? This is a I, this is a j, x. But I want to tell you that, and with this we are very familiar. Huh? We know what is this. Actually, for example, in this room, for example, if you give it the coordinate system, so this point will be the coordinate will be 0, 0, 1, and this one will be 0, huh? 0, 1, 0, and the other. So you have a very good intuition about that. Good intuition, good and easy thinking, easy understanding. But not always we have some simple case like that. I told you this is vector for me. I can have the object and I can write the object in terms of that. And I can call it this vector. And you can use the same symbol as I use it for the. But the problem is that this object is not the normal vector. Huh? This is a vector matrix, something like that. It seems that because you have a matrix and you compress the matrix inside the object, and I call it this vector. Anybody of you, can you remember any example in physics that you have a vector but the component is the matrix? You remember?
Gray. Gray.
No? Again, thanks to the quantum mechanics, we have something called a spin.
Yeah.
A spin is a vector. I mean, a spin should be like that. But each component should be measurable. And to be measurable, each component should be matrix. Well, just as simple sentences I told you. In quantum mechanics, if you want to have a vector matrix, you needed to have first a vector form. I mean, it should be some vector really. But the components should be measurable. And to be measurable, you should have the matrix. And this is a set of the functions. So for each n, you can plot this function. So I don't think that this is very hard to understand that the meaning of this function. Just give the n and you will have the function. But do you know what's interesting? The interesting is that they appear as the solution of some equation in physics. Like the Helmholtz equation, like the Schrödinger equation, like the wave equation, like everything. And again, they implies the existence of some quantity, some physical quantity, and this physical quantity should be measurable. So for that reason, we can call it this some kind of the vector space. They live in the vector space. So let me start to explain what's the vector space, because we just repeated that. So the postulate of the for vector space. Give me a set of the element, anything, like, I don't know, like the star, anything. I mean, anything mean anything, even that. And give me one more symbol, I don't know, this. So there are 4 elements here. I can call it this V1, V2, V3, and you can continue as long as we want. Just when I can call it this vector space is that if I make a combination of that, this combination, I can call it this set V, for example, or A. This combination should exist over inside there. So this means that inside. We don't know that the rule and also the minus. We don't know that even the plus is enough. And C1 and C2 should be 2 numbers, just the real, just number. real numbers.
The second one, the derivative of V2?
No, any derivative. It's just some symbols. I told you, just some symbols.
No, the dot, I see the dot.
Is this? This?
Above the V2.
Above the V2. No, there is not any derivative or something. Nothing. Just a normal one. Okay. This is the equation, but I want to explain you in the detail. So I mean that, let me to say that, so for example, you have you have a V1, just as the normal vector, as you know, the normal mathematics. So to make the name of the vector space, you need to add these two vectors, and you know that how to add the two vectors. And if the add again existed inside the system, again existed inside this set, you can say that you have a vector space. And you can combine this by the number. So for example, 2 double of that, this is a 2v1 for example, and that can be for example 2v2. Again, if you know this is this graph just to explain easily. So if you just combine any combination of the vector and still remain inside the set, so you can call it this as a vector space. For example, not this example needs one more advanced. To have a vector space, or to work with the vector, also you need to know the concept of the component, or the unit vectors. So in physics, measuring is not possible if you don't have the unit. You have a unit for everything. For the vector, you should have also the units. So you needed to know that how many elements you need for your system. So I don't write anything here because I don't know. Any example will be confusing you. You need it first. You need to find or count number of the basic elements you needed. You need to explain your system. And for each of the elements, you need to define one unit vector. For example, if the particle is moving over a closed set like that, so this is the particle, one particle is moving, mass m for example. So you know that at each point, what is important for you is the distance, and what is important for you is the theta, the angle between that and this axis. So you have a 2 coordinate here. For each coordinate, you need to define a unit vector. So in the direction of the r, I need to define a unit vector. I call it ur or er. The length of this vector is 1, the vector of this element. And you need to know also the unit of the vector, or the unit of the measurement in the direction of the theta. So, for example, you can call it this E theta. So in this simple example, you needed just two simple vector, simple element actually for your measurement. But not always it's 2. You can have more than 2 elements, and to describe some system, you needed more than 1 unit. This element with the symbol is called unit. I can call it vectors. They have just one property. The property is that their length of each one is 1. Because that was a guarantee. Say that was a protocol. Say that for measurement you need to know the unit. So this is the unit. So the length of each vector will be 1. So this is, and I didn't define that what is the length. So far I didn't define. To define the length, you needed to go through the second property of the. So the first property is that they should be closed. I mean, if you take 2, so the combination of these 2 should be existed inside that. So you needed, the second one is the existence of the unit vectors. So you need to have the unit vectors and then the length. For the length, you need to define the length. So you need to define some element called inner product. Inner product. Or dot product. I write here define because you know how to define the dot product of 2 simple vectors before in the mathematics, you know that. But not always. If you have a vector, for example, if you have a function, like if you have a matrix, how you will do that? Well, the simple vector like A, for example, if you use a coordinate system, a unit system like that, you can write it. Why I can write this equation? Do you know? This is a guarantee from here. No, the unit vector combined together by some constant like A1, A2. Still, I am hooked that this combination is an element of this space. I mean, if I make the combination, I will get that. I should not get something outside of that. If you have a 2-dimensional system like that, if I make a combination and I get some vector outside of that, you understand me? It means that these 2 vectors don't make the vector space. You needed one more element to complete your set of the unit vectors. So with 2, you cannot have that. This is outside of this system. They are not closed actually. But these three elements can make a vector, and I write it this vector. And this is, thanks to this, I write A1, A2, A2. These are just numbers, you know. Each of them is called the component. Component of the A in direction E1. This is the easy, because most of this information you read it before in different course. So this is the, but I will improve that. So later I will use the function instead of the vector. So you will see that the dot product will be very complicated. The component interpretation will be very complicated. So you need to define the dot product. So the dot product between vector A and each element gives you the component of the vector in that direction. So if I have a that E1, and if this is my vector A, so just make the projection. This is the projection, normal projection. So the projected length is A1. So this is called the component of the vector, component of the vector in direction of the E. And you can make it the projection different and get it as A2. And if you have 3 axes, you can do that for 3 axes. I don't want to make it for 3 axes. This is the definition of the inner product. If I have a 2 vector like A and a B, look at that, how I can make that. So I can write that like A dot, what is the B? B is B1, E1, Exactly. Because this is I don't know you get my point on that. No. I give that, and I will continue with that. I never talk about that even more. I say that this is the representation of the vector in this basis, And I will use that. I will use that. this is the postulate method to learn the mathematical physics. Postulate means you accept some principle, okay, and you continue with that. I accepted that it should be some unit vectors, huh? And they need, because we need to do measurement. So for measurement, you need the units, like the normal units. I say that this is a representation of the vector in these units. And you should not have more because you have a 3 basis. So you have a 3 E1, E2, E3. And just simple combination. If I put these together to that, this is a new object. Okay? How you can be sure that this object exists inside that, huh? The only thing exists inside the space is something proportional to E1, something proportional to E2, and something proportional to E3. I mean, 2 E1, for example, 1 E2 minus E3, or something like that. You cannot have like that. But this is existed. And we needed that. This is a new object. Yeah. Or tensor. And I will spend enough time later to that. Not any combination is welcome for us. Now look, I just use this definition, okay? I didn't prove that, huh? I say that component of the vector in the direction of E1 is that. Just accept this definition. And look at that. By this definition, I want to find the inner product of 2 vectors. Okay, you think that this is the number? Yes, this is a number. I can put outside of all of them, huh? Just I will have that. And the same I do for the other one. This is the one I want to try to motivate you. I want you then to think about the physics concepts and the mathematical engineering problems like that, like the postulate, by the principle. So I make it this principle for you. According to this principle, it's A1. Huh? According to this principle, just change the angle. This is the A2, and this, according to that, this is the A3. So the inner product of 2 vectors is just AIBI. Are you feel comfortable with this notation or no? It gives you just the sigma from 1 to 3. You can put it 1, 2, 3 and get it. So this is the definition of A and the B dots. Do you have any question so far? So, thanks to this, okay, this is also can written E1 multiplied to O, okay? For normal vectors, I mean, not for something in quantum mechanics. When the algebra is commutative, I mean, when A dot E1 is equal to E1 dot A, everything is perfectly easy. It's very perfectly worked. But not in quantum mechanics. In quantum mechanics, if you change the position, everything will be changed. So that's not our business now. So now let me to define the length. Define the length norm of a vector field. A vector. So the norm of the vector is given by this symbol. So there are different symbols for that. It's just given as A dot A. So A dot A is just means that AI, huh? So sigma AI squared. Okay, it is easy, and you see that definitely that will be positive. Huh? So you never can get any vector in the Euclidean geometry with a negative length. Euclidean geometry means that when your geometry is the geometry you use in the classical mechanics, x, y, z, and so on. But what happens if the vector is a complex number? Huh? If the vector I is like that, what you will do? and I is radical minus 1. Our vectors are the real vectors. For the complex vector, you needed to change this definition. I want to do the change now, and later I will use. I don't want to postpone the change to the later. So I will tell you that this definition is perfectly good if AI is the real number. Huh? Like 1, 2, 3, minus 1, minus 2. If you have a complex number, the norm of the vector, sorry, this is a norm of the vector is the same. Just you needed to a little bit change that. Instead of the one of them, you needed to define the complex conjugate of this quantity. What is the complex conjugate? You know that if you have a complex number like that, so complex conjugate is just I minus IB. So just change it by 2. So from the